Okay, hello and welcome to today's video. It's a video about the angular velocity of precession of a gyro. Okay, consider the following situation. I've got a spinning disc spinning at angular velocity omega radians per second. The disc has a radius small r and it's situated at a distance from a fixed pivot point, big R, away from that fixed pivot point. Now, using the right hand rule, as the disc spins that way, anti-clockwise as I'm looking from this side, we'll get an angular momentum vector L going along there, alright, perpendicular to the plane of rotation. Now, gravity acting downwards from the centre of mass of the rotating object acts a distance away with a moment arm of r, and it's going to create another torque. And using the right hand rule again, this torque will be acting into the page. Okay, I can't draw that into the page, but imagine the torque caused by gravity causing a torque about this pivot point here would cause the whole thing to want to travel down that way. So that causes a torque acting into the page. Now, that applied torque will cause a change in momentum with respect to time here, and it will cause the object to point in a new direction, or the spin axis will point in a new direction because of this change in angular momentum. Okay, and that change in angular momentum will cause an angle here. It will cause the object to change to a small angle over a certain amount of time. Okay, d theta by dt. Then I can say for a small angle, like if this angle's really small, it's the angle's changed over a tiny amount of time, that angle is basically very close to tan theta, which is opposite over adjacent, which is this side divided by that side, which is the change in momentum, angular momentum over time multiplied by 1 over the original angular momentum. Okay, that's just opposite over adjacent for your tan function. Right, next I can say that the change in angular momentum over time is the same as the torque, which is the same as the force times the moment arm, which is mg times r. That's this part here, the moment arm times the force. Alright, so dl over dt is mg big R. Now L, the angular momentum of the spinning disc, the angular momentum equals the moment of inertia times the angular velocity. The moment of inertia for a spinning disc is mr squared over 2. So the whole thing becomes mr squared omega, or the angular velocity of the disc, divided by 2. Okay, so going back to this original equation for d theta by dt, which would give me the angular velocity of the precession of this gyro. It's going to spin round in like a horizontal plane parallel to the paper, sort of defying the gravity that's trying to pull it down. So if I combine these two terms here, I get me dl over dt equals torque equals that. I get me angular momentum equals this, but it was 1 over angular momentum, so I need to spin that upside down. And I end up with these two terms here multiplied together. The masses cancel, and I ultimately end up with this then. So if my d theta over dt, which is the angular velocity of the precession of my gyro, all comes down to this quite simple little formula here. It's 2 times gravity times the distance the pivot point is to the gyro, or the moment arm for the gravity, divided by the radius of the disc squared and the angular velocity of the disc. So what does this mean then? It means to make the object precess faster, I can either increase gravity, we take the gyro to Jupiter with more gravity, that'll make it precess faster, or situate the gyro further away from the pivot point there. I could put the gyro over here, make r bigger, that'll speed up its precessional velocity. If I increase the radius of the disc, that will slow down the precessional force, the precessional velocity quite a lot because it's a squared term. So if I increase the size of the disk, the angular velocity of precession will decrease. Also, if I speed up the disk, the thing will precess more slowly. Okay, it's a good topic this. It's a lot of angular momentum vectors. It's crazy vectors that are normal to the plane of rotation. It's a good topic. But that's one way you can derive the formula for the angular velocity of precession of a gyro. Okay.